the collisions are really occurring very, very near the speed of light. And an interesting thing occurs when an object gets accelerated near the speed of light. Einstein, in fact, taught us in 1905 that if you take any object, so now here's a gold nucleus, which has a radius of about 6 femtometers, and if you accelerate it at a particular velocity, you can construct this quantity called gamma, which is the Lorentz gamma factor, and actually, to any observer, the object looks compressed along its direction of motion. And so the size, the radius along this direction, which is moving this way, is actually divided by gamma. And so now, when we accelerate the ions at Rick to as much as we do, which is actually to 99.995% of the speed of light, that's about 100 times compression. So you've taken this round object and then compressed it 100 times along its direction of motion, essentially making them into flat pancakes. And so we've got some interesting computer models. These are relatively old, but they're good to show basically what's happening. These are these compressed pancakes of the nuclei hitting each other head-on. The units of time are femtometers over c, as I mentioned before, so these are very, very rapid, although it looks very slow here. And what you're seeing is the energy of the nuclei is being turned into thousands of degrees of freedom, which are interacting with each other, potentially creating this new state of matter, which is the quark-gluon plasma. But eventually, as the system gets more dilute, the interactions turn off, and the particles turn into the normal particles that we know of, which then stream toward our detector. And this is what we see in the final state, these particles streaming out toward the detectors in our lab. And so, like I said, this is in some sense a real sort of real-world example of turning energy into mass. You've actually traded the very fast nuclei into much slower particles of other types. Of course, it's always important to ask yourself how much energy is in each of these collisions. It looks like a lot of stuff is going on. You can actually calculate in terms of joules. You write down the number of nucleons, the nucleon-nucleon energy, and then a conversion factor. You get a head-on Rick collision has at most about 6 microjoules. And this is a sort of favorite comparison. If you consider 2 mosquitoes flying around like this, and you consider them flying at each other and basically stopping, say heating the air in the process, you can write down the kinetic energy of the 2 mosquitoes, and that's about 1.2 microjoules. So it's actually only about a factor of 4 or 5 different. So keep in mind that although there's a lot of activity going on here, the amount of energy is actually quite small.